Welcome everyone to another lecture for second year physical chemistry, and today we will discuss ionic activity. What will be covered and why? As we explored ways to understand non-charged activities via a model and excess functions, one can also use models to predict and understand ionic activities. And as a result, I will introduce to you the Debye-Huckle model. What you will need. You'll need Atkinson's physical chemistry, under the section of simple mixtures, activities, and naturally previous lectures on the chemical potential. So let's start off with a bit of history. We'll talk about Debye. There is his picture. Peter Joseph Willem Debye, or as they would say in Dutch, Petrus Josephus Willemus Debye, was born in 1884 in the Netherlands. He died in the USA in 1966, and he won the Nobel Prize in Chemistry in 1936. He is one of the greatest physical chemists of all time, and he discovered the concept of the dipole moment in asymmetric molecules. Did loads of other work, provided contributions in understanding low temperature heat capacity and the idea of phonons, and he worked quite a bit on X-ray and light-based techniques. One of his students was a guy by the name of Huckle, Erich Armand Arthur Joseph Huckle, born in 1896 and died in 1980. He was a German physicist and chemist, and you may have heard of him, and that he helped develop molecular orbital theory. So with Debye, he helped establish the Debye-Huckle theory in 1923. So this model we're going to cover today has been around for quite a while. So Debye-Huckle theory. So Debye and Huckle derived an equation to estimate the activity coefficient for ions. Now this model, it assumes that the central ion is surrounded by a cloud of oppositely charged ions. So for example, if you've got sodium plus, you would expect a bunch of chloride 1 minus ions around it if you've got a solution of sodium chloride. And this cloud is like an encapsulating sphere around the central ion. And the solvent as such doesn't exist as molecules, but more as like a background with a particular dielectric constant, which in the picture you see below, you can think of as this blue amorphous background. I'm not going to go through the derivation, it is quite involved, but what you can get out is the following equation, which if you derive it in terms of rational units is the logarithm of the activity coefficient of your ion is equal by this prefactor, in which you've got your charge, Z, the fundamental charge, E, kBt, which is Boltzmann's constant times temperature. You've got epsilon naught, which is the permittivity of free space, and epsilon, which is the dielectric constant of your solvent. And you multiply this prefactor by this bracket, in which you've got kappa divided by 1 plus kappa AD. Now, kappa squared is equal to a prefactor as well, which is very similar to the one above, plus this summation term. Now, what's AD? That's the radius of your ion species. And Ni in this summation term is the number of ions of species I surrounding the central ion per volume. And that's the volumes in meters cubed. And Z is the charge on those ions. So for example, if you have a sodium ion in the middle, you're interested in it, you will then, and you've got a bunch of chloride ions and other sodium ions, what you would do with the summation term is you will count the number of sodium species and you would multiply it by the charge on that species, which would be +1. +1 squared gives you 1. 1 times the number of ions, that's your first term. You do the same for your chloride ions, but you'll use -1 for the Z. But as it turns out, the Z equals -1, you square it, you get 1. Things get a bit more complex when that Z term has to become something like a 2 plus or 2 minus to account for ions such as copper 2 plus. But you generally get the idea. It's a summation of all charged species in your solution, where N is the number of ions and Z is their associated charge. However, when we do experiments, we don't tend to do things in rational units. We tend to do things in either molars or molality. Here is the equation for molarity. You get the same equation as before, but you adjust the kappa term to include Avogadro's number. And instead of Ni, you now have Ci, the molar concentration of ions or species I surrounding the central ion. And you can do this for molality, where instead of concentration in terms of moles per liter, you can do moles per kilogram. This naturally changes ever so slightly your values for kappa, but that's the basic idea. And this brings us to an important concept called the ionic strength. From the previous slides, you may have noticed this term, 1 on 2 multiplied by the summation I Ci Zi squared. This is referred to as the ionic strength, or I, and you will come across it quite often. Hence, from the above, if we make this definition the ionic strength, you can rewrite the Huckle equation to look like log gamma equals minus a fraction, with the top of the fraction equal A, Z plus Z minus absolute, multiplied by the square root of I, divided by 1 plus B root I, where A takes a particular value, which is 0.509 per mole, the root of, and then liter to the power 3 on 2. And B is a dimensionless constant depending on the ion on question. Different ions have different ionic radii, so that B is going to change. Now, it's important to note that these constants are also dependent on your solvent and your temperature. And the value for A I've just quoted is for a water solvent at 25 degrees Celsius. Now, why is it solvent dependent? It goes back to the dielectric constant. This value is calculated for a dielectric constant for around 80, which is what you have for water. By the way, that happens to be the same dielectric constant as for heavy water. Now, we're going to discuss the limiting law. In the limit of low concentrations, you can rewrite the Debye-Huckle law very simply as log gamma equals minus A absolute value of Z plus Z minus root I. A very simple equation. The value for A is still the same as I quoted before, provided it is water at 25 degrees Celsius. So overall, the activity of an ion is determined by the concentrations of charges around an ion at constant temperature. Alright, what are the key concepts I want you to take away? The Debye-Huckle theory can estimate theoretically the activity of an ion via accounting for the concentration of charges around the ion. And that's the equation you can remember. In the limit of low concentration, it becomes log gamma equals minus A absolute Z plus Z minus root I, where I is the ionic strength. As such, this brings the lecture to a close, and we have our lecture quiz. And there are 3 questions, all multiple choice. I'll read them out for you. Question 1. Imagine you have a solution of NaCl in water, table salt in water. You use the Huckle law to determine the activity coefficient of Na+. You now calculate the activity of Cl-. Is the activity of Cl- A, the same as for Na+, B, more than Na+, C, less than Na+? Question 2. Imagine you have a solution of NaCl in D2O, that is heavy water. Can you use the value of A equals 0.509 mole to the minus a half liter to the power of 3 on 2? Yes or no? Question 3. Imagine you have a solution of NaCl in ethanol. Can you use the value of A equals 0.509 mole to the power of minus a half, or times liter to the 3 on 2? A, yes, or B, no?